Hey guys, today we're taking a look at quadratic regression. Now remember back to last semester we did something called linear regression, and we took a data set or a set of data points and we plotted them on the coordinate plane, and we said, hey, let's come up with a line that fits that data. And when we did that, we put that into our graphing calculator and we did a stats linear regression, and it came up with the equation for a line that models that data, and that was known as the regression line. Well, today we're going to do quadratic regression, which means we're going to model a set of data points. However, instead of a line, it's now going to form a parabola, and that parabola is going to take on the equation of a quadratic, which is y equals ax squared plus bx plus c. So let's take a look at a few examples and see how we can do this on our graphing calculator and by hand. Our first example says we're going to make ordered pairs of these polygons and their diagonals. So first off, we have a triangle. It's got 3 sides but 0 diagonals. And next one, we have a 4-sided quadrilateral, and it has 2 diagonals. Next, we're looking at a pentagon with 5 sides, and actually it's going to have 5 diagonals as well. And therefore that ordered pair is 5, 5. And finally we have a hexagon that's got 6 sides and 9 diagonals. So let's make sure we get all of our diagonals in here, and there we have all 9 of them. So 6 sides and 9 diagonals. Let's make a table of those ordered pairs just like any other table we would make. And then finally we got 6, 9, and then let's go ahead and graph those. So we got 3, 0, 4 over and 2 up, 5 over and 5 up, and then finally 6 over and 9 up. So you can see by looking at these data points, they kind of fall in a straight line, but more likely they fall in this very steep ascending curve. And so that's what we're going to do, is we're going to find a quadratic regression that models these data points, and now we can do that on our graphing calculator. So keep this ordered pair here in mind, and what we're going to do is go over to our graphing calculator now, and we are going to take a look at entering this data into our graphing calculator. So go to stats, and then we're going to go over, down to edit, which we already have. We're going to edit list 1 and list 2. Now list 1 will be our independent variables, or our number of sides. So that will read 3, 4, 5, and 6. Next, we're going to arrow over to list 2, and now we're going to put our dependent variable, which is our number of diagonals. And if you remember, that went like this: 0, 2, 5, and 9. All right, so there are our data entered in there. And now we're going to go back to stat, and now we're going to arrow over to calc. And if you go down in here to number 5, you see that says quad regression. So we're going to press enter on quadratic regression, and it's going to ask us what we want for list 1 and list 2, or independent and dependent variables. Just go ahead and keep pressing enter because they're in list 1 and list 2. And you can see here now that it's going to give us the values for A, B, and C. Now let's just take a look at this so you can see what we're looking at here. Quadratic regression. It's going to follow this form of y equals ax squared plus bx plus c, and it's going to tell us that a is 0.5, b is negative 1.5, and c is 0. So what that means is our quadratic regression that models this data fits into this format here: y equals 0.5 x squared, and then minus 1.5 x plus 0. Now we don't have to include the plus 0, so we'll just keep it right here, and we'll say that this is the data that allows us to model the number of diagonals for an n-sided polygon. So a little bit further down it says use this model now to find the number of diagonals for a 10-sided polygon. So we're going to let y, remember, is our diagonals, and x here is going to be the number of sides of our polygon, so we're going to insert 10 in there, minus 1.5 times 10 again. Okay, so 0.5 times 10 squared, well 10 squared is 100, times 0.5, that's going to give me 50, minus 1.5 times 10, well that's going to be 15. So y, remember, is the number of diagonals, so our number of diagonals here is that y equals 50 minus 15, which is 35 diagonals. So a little extra credit here for you. Go ahead and create a 10-sided polygon and show me all 35 diagonals. All right, let's move on to example 2. Now, here's a way that we can calculate our regression model by hand. So it says a parabola passes through the points -1, 8, 1, 2, and 3, 4. Find the equation of the quadratic that fits these points by solving a system of equations. So let's go ahead and plot these points. You got -1 over and 8 up. You got 1 over and 2 up, and then finally 3 over and 4 up. So it looks like our parabola does something like this, and we want to come up with the equation for that parabola. Okay, so it says to write a 3x3 system and solve it. Now remember, these ordered pairs here are xy, xy, and xy. And our quadratic equation should fit into this: y equals ax squared plus bx plus c. So what we're going to do, they're going to take each ordered pair and remember this is set equal to y, and we're going to substitute in our values for x and our values for y and come up with a 3x3 system. So this first order pair should read like this: 8, that's my y value, is equal to a times -1 squared, because that's my x value, plus b times -1, sorry, and then finally plus c. My next order pair should be 2, because that's my y value, is equal to a times 1 squared plus b times 1, because again those are my x values, plus c. And then finally my last order pair should read like this: 4 is equal to a times my x value squared, which is 3 squared, plus my b value times my x plus c. Okay, now let's go ahead and simplify this system of equations. So what we have here, whoa, that's a bad looking, there we go. There, curvy brackets, there we go. That's better. So what we have here is 8 is equal to -1 squared is 1, so that's 1a, plus -1 times b, so that's really -b plus c. Next we have 2 is equal to a times 1 squared, which is 1a, plus 1 times b, which is 1b, plus 1 times c, which is simply c. All right, now our next and final equation then should read like this: 4 is equal to a times 3 squared, which is 9a, plus 3b, plus c. Now we have a system of 3 equations and 3 unknowns, and we're going to solve for each one of those equations. And one of 2 ways we can do this: we can use our inverse matrices. So if you remember how to do that, we're going to take our coefficient matrix, which looks like this: 1, -1, 1, 1, 1, 1, and then 9, 3, and 1. That's our coefficient matrix. And then we're going to multiply, or sorry, we're going to take the inverse of our coefficient matrix and multiply it to our constant matrix, which in this case is 8, 2, and 4. Now, when we do that, we multiply it by 8, 2, and 4, we will get the values for A, B, and C. Now, when we do that, plug that into our graphing calculator, and we end up with the values of 1, -3, and 4. You can go ahead and test that just to make sure that is in fact the case. And so that means my A value is 1, my B value is -3, and my C value is 4. So the equation that models this parabola should read like this: y is equal to 1x squared minus 3x plus 4. And again, if you go overhead and go into Desmos and take a look at the graph of that equation, x squared minus 3x plus 4, you should see that it passes through these 3 points: -1, 8, 1, 2, and 3, 4. All right, let's move on to example 3 now. In example 3, it says a batter hit a ball that was 2 feet off the ground directly above home plate. It was about 12 feet off the ground when it passed over the pitcher's head 60 feet away, and it was caught 4 feet off the ground by an outfielder 300 feet away. So let's just kind of sketch out this parabola here and see what this really would look like. If we're talking in terms of distance away from home plate, then right at home plate, the ball was about 2 feet high. 60 feet away from home plate, the ball was about 12 feet high, and then again out here at 300 feet, the ball was about 4 feet high. So this parabola is going to kind of follow this path that looks something similar to this dotted curve here, and we want to find the quadratic equation that relates the height of the ball to its distance from home plate. So h is going to be our dependent variable, and d is going to be our independent variable, because the height will depend on the distance it is from home plate. So what we're going to do is use our graphing calculator to do this one. So go ahead and switch back over to your graphing calculator. So we're going to go back to our stat. Oops, I hit stat. And then we're going to edit our lists 1 and list 2. Remember, you can arrow up and highlight the entire list to clear it. And then in list 1, we are going to put our distance from home plate. So our first height we have is 0 distance from home plate. The second height we have is 60 feet from home plate, so we're going to make that a 60. And then the final distance or height we have is from 300 feet away from home plate. All right, now let's head over to list 2 here. In list 2 we have 2 feet off the ground, and then 12 feet off the ground, and then finally it ends up at 4 feet off the ground. So once we have those data points in, we can go back to stat, arrow over to calc, and we're going to calculate our quadratic regression model. Press enter, and here are the values for that equation. Okay, and here is the equation of our line. We have the height is equal to negative point, and if you take a look here, that says e to the negative 4. So that's going to be negative 0.00067 x squared. And then we have, let's erase this here and see what we have. Yay, okay. We have plus 0.206x plus 2. Alright, so the equation of our line here looks like this guy here. And now we want to know the maximum height the ball reaches in its travel out to the outfield. Okay, so a real cool, nifty way that we can do that is again by using our graphing calculators. And so we're going to go to our y equals. And now remember your variables key. Let me just clean this up here a little bit. Our variables key here, if we press variables, we're going to go down to statistics, and then over to EQ, and that first option there is our regression equation. So go ahead and select that regression equation, and it plots it right there for your y equals. Now, we're going to change our window here. So remember our x maximum was right around 300. So let's go ahead and make that 330. We'll make our x scale jump by 15s. And then our y max, let's just make it like 25. We're not really sure the maximum height of our ball, but we think 25 will be about good. And then we'll make our y scale jump by 2s. Okay, so let's take a look at the path of this ball up here into the outfield. There we go. It's a nice little curve. Now we want to find the maximum height that ball reaches. So in order to do that, we can use this trace function, or the calc function I should say, which can be found under second function, trace. And we're going to go down to maximum. So select maximum. And now what you'll notice is that your calculator is asking you to box in where that maximum point occurs. So it says left bound. Okay, so we're going to use our thumb pad here to arrow left and right. So left bound means to put your cursor on the left of that maximum point and press enter. Now you'll notice it says right bound, so we're going to move over to our right side of our maximum point and press enter. And you can see the calculator is giving you these little arrows pointing in. Hey, it's saying the maximum is in between these two arrows. So now finally it says guess, so go ahead and put your cursor as close to where you think the maximum point is and go ahead and press enter again for a third time, and it gives you the maximum point exactly. So we'd say our maximum here is the vertex of this parabola, and it occurs at when x, which is our distance here, is at 154.9, and our y is at 18.0.